Hi everyone, it's an honor to be here. My name is Yonatan, and I'd like to talk to you today about test set contamination. So recently, we've seen large language models show remarkable performance on many challenging benchmarks. And it seems like almost every week, there's a new open source model which comes out and tops the leaderboards. What's driving this performance gains that we're seeing in unsupervised learning has been massive pre-training data sets collected from the internet. So to give just one example, here's a breakdown of the pile. This is a large, diverse data set, which many open source language models use for training. And you can see it's compiled from many different sources. So here in blue, we have academic sources like Archive and PubMed. In green, we have internet-based sources like Wikipedia and Stack Exchange. There is prose in here, there is code and math, and so on. But because of the scale of modern pre-training data sets, which are often on the order of trillions of tokens or petabytes of data, it's difficult to know if there's good separation between the training process of the language model and the benchmarks that we evaluate on. So to give you an example of how contamination might play out, let's say you have a language model that you want to evaluate on a coding task, like code forces, for example. So code forces is a very commonly used benchmark, and maybe somebody uploaded it to GitHub, and then a web crawler found it, and as a result, it ended up in your training data. And so when you see an accuracy number or score on some benchmark, it's difficult to know if that's a result you can really trust because of the risk of contamination. So naturally, this brings us to the following question, which is how can we identify when a language model has trained on a test set or benchmark? And this is a difficult question to answer because many of today's top-performing LMs are either closed behind APIs, or even if they're open source, their data sets are kept secret. So this is a figure from the Foundation Model Transparency Index by Stanford CRFM. You can see here in the first row that when it comes to pre-training data, there is very little openness in the industry. I want to show you an example of the kind of discourse that's happening around test set contamination today. So these are screenshots from a very prestigious academic forum. It's called Twitter. So on the left, Horace is saying here, isn't it suspicious that if you look at the performance of GPT-4 on code forces problems introduced before 2021, it scores 100%. But if you test the model on recent problems, the performance drops to 0. Yeah, that seems a little bit suspicious. On the right, Susan points out that if you give Phi 1.5, so this is a language model trained by a team at Microsoft, if you give Phi 1.5 the first half of an example from a data set of math problems called GSM-8K, it'll complete the second half perfectly, which also seems a bit suspicious. Of course, it's possible that these things happen by random chance, but the point is that this is circumstantial evidence at best, and it's clear that we need some way to audit or test a closed language model for contamination in a way that provides rigorous proof. So there's been a lot of exciting work on test set contamination recently. I want to highlight 3 works in particular that are actually all at ICLR this week, and I would highly encourage you to meet with these teams and learn more about their work. These are all excellent papers, but for our work, we were specifically interested in detecting contamination with provable guarantees in the false positive rate. And that's what I want to talk to you about today. So the question we're interested in is it possible to prove in a statistical sense that a language model was trained on a test set without access to the data used to train the model? So to describe this goal more formally, our setup is as follows. So we're given some test set X and the ability to evaluate log probs of text under a language model theta. And what we want is to develop a statistical test in the classic frequentist sense, which guarantees the type 1 error rate of at most alpha. So here, we're framing contamination as a statistical dependence between the model and the test set. And what that means is that we're going to test the null hypothesis that the test set X and the model theta are independent random variables. So just to be precise, the randomness of the model here is determined by the random draw of the training data, which may or may not contain the test set X. So how can we do this? How can we accomplish this? In order to make this possible, we're going to exploit a property which is true of many test sets, which is called exchangeability. So what do I mean by this? So typically, a test set is just a file where on each line we have an example. But the order in which the examples appear in the test set doesn't actually matter. The examples are exchangeable. I can show you the examples in any order and it's still the same test set. So formally, what exchangeability means is that we can permute the examples in the test set without changing the joint distribution of the data, which means that the model should have no inherent preference for the ordering of the examples. It's worth noting that exchangeability is a strictly weaker assumption than IID, which is an assumption we make all the time about our data and machine learning. So however, if a test set was leaked into a model's training data, because of the way pre-training works, where we take as many tokens as fit into the context window, the model would see multiple examples in a row and then memorize something about the order of the examples in the test set. So our key insight here is a preference by the model for a canonical ordering of a test set must be a result of contamination. So using this idea, there's a very simple permutation test we can construct. So the key here is to compare the likelihood of the original ordering to the likelihoods of shuffled orderings. So for example, for the original ordering to have the highest log likelihood under the model than any ordering over, let's say, 1 million random shuffles, there's a 1 in a million chance of this happening under the null hypothesis, right, if the model didn't see the test set during training. So more formally, we can draw random shuffles, which is shown here as x sub pi, and we can compare each of these shuffles to our original sequence order, which here is log p sub theta of x. And by doing these comparisons, we're estimating the quantile of the log likelihood of the original ordering. So this ratio here turns out to exactly be the p-value of a permutation test. So this test works quite well, but it's computationally expensive because of the number of times we need to permute the data set. And it turns out that we can do something a little more clever by aggregating a number of smaller tests, and that's what we call the sharded rank comparison test. And just for the sake of time, I'll refer you to the paper for more details. So how well does this actually work in practice? So in order to validate our test, we needed to have a language model for which we knew the training data was contaminated. So we decided to train our own model. So we started with a data set of 20 billion tokens from Wikipedia, and we pre-trained a 1.4 billion parameter language model on this data set. But first, we took a collection of benchmarks and we injected them into the training data at random positions. And then we wanted to see, so can we actually detect contamination in this case? So here are the results of that experiment. They're in this table. So here, each row is a test set that appears in the training data. And the data sets were injected at various duplication rates. So some of them are in there 1 time, some are in there 10 times, and so on. And in the 2 columns on the right, we have the results of both the permutation test and the sharded test. So these numbers are p-values. So the smaller the better, or the stronger the detection. And using a typical rejection threshold of 0.05, we find that for test sets which appear 10 or more times in the pre-training data, we can detect them 100% of the time. So we get perfect detection. We also found that detection at a duplication count of 1 is quite challenging. So we don't currently have a statistical test that works for duplication counts that are that low. And we'd like to encourage the community to continue working on this problem. So one question you can ask is, at what point does contamination become detectable? So we found that for a duplication count of 4, we can detect test sets about half the time. For duplication count of 2, we can detect test sets some of the time. So we are able to detect contamination at low duplication counts, but just not for duplication count of 1. So you're probably asking yourself, okay, what about real models? Can we identify provable instances of contamination in LLMs that are in wide use today? So before discussing these results, there are a couple of important points I want to make. The first is that absence of evidence is not evidence of absence. So just because a p-value is high doesn't mean that there's no contamination. It just suggests that contamination is unlikely, at least at high duplication counts of more than 10. So it's a very particular claim that we're making here. The second is that there are a lot of hypotheses being tested here, and it's possible that some of these p-values will be significant just by random chance. So it's typical to do what's called a multiple hypothesis testing correction, and I'll refer you to the paper for discussion on that. So our first result here is that we didn't find evidence of contamination other than of Mistral 7b and ARC-easy. And with a multiple test correction, the p-value is just barely below significance, but it's still significant. The second result here that's of note is on MMLU. So the MMLU row, you'll see, has a little dagger there. And the reason for that is because some of the test sets in MMLU were not exchangeable, and we had to filter them out. So it's not quite the same as the others, but our findings are consistent with the Llama 2 report, which finds mild evidence for contamination by MMLU in their pre-training data. So I think the main takeaway here is that it's probably not the case that popular benchmarks are being duplicated numerous times in the training data of top-performing language models. Instead, it's likely that if these test sets appear in training data, that they appear at low duplication counts. So then the question becomes, how much does low duplication count contamination affect performance on benchmarks? I think this is hard to say, but in some sense, this work suggests that there's an upper bound on how much contamination is out there for today's highest performing language models. So to conclude here, we covered 3 important points today from our work. First, we showed that it was possible to get provable guarantees on detecting verbatim contamination by leveraging exchangeability in benchmarks. So this is exciting because it opens the door to potentially very principled approaches to contamination audits. Second, we showed that these tests are effective, but there's also a major open problem that we can all make progress on, which is contamination detection at a duplication count of 1. Finally, we tested existing public language models and don't find evidence of contamination, at least with high duplication counts. And this could be due to a number of factors like deduplication being very common these days, but addressing the case of duplication count 1 would allow us to give more conclusive results on public audits. So we think this is an exciting first step and would like to see others make progress on low duplication count detection. And all of the models and benchmarks used in this project are available to encourage the development of future work. Finally, I just want to acknowledge my co-authors for their hard work and Stanford CRFM, especially David Hall and Percy Leong, without whom we wouldn't have had the compute for this budget or the compute for this project. Thank you very much.